Today I'm going to talk about the topic of field weakening in motors. We've got an induction motor connected to our variable speed drive over here. So as per my previous setup, I've got the current probe going through one of the phases, and I've got that connected to my scope over here. So what I'm going to do is I've set this up so that it can run up to 100 Hertz. In other words, we're going to run super synchronous. So we're going to run this motor into what's called the constant current region, constant power region, which is when you go above base frequency, which is 50 Hertz. Because beyond that your voltage stays constant and your current decreases. So you're going to see the current waveform change there on the scope. So let's get that set up so you can see it. You can watch the frequency. So there I've started it, and you can see we're at 12 Hertz. Now if I turn that all the way down, you can see the current, about 200 millivolts per division that we're running at there. Now I'm going to increase it to 50 Hertz with my potentiometer. And you can see that we're still at 200 millivolts on the current. Now I'm going to take it up to 100 Hertz. See what happened? The current has halved. We're down to about 100 millivolts. So now we're in what's called the constant power region. So stop that. Stop our motor. So what's happening here is that the speed increases but your torque decreases, so therefore you've got constant power coming out. So your current comes down, your voltage is staying constant after 50 Hertz, and I can show that by going to pyramid over here. That's the output voltage. So if I slow it down to the point where we see it just starting to come down on voltage, we should be at base frequency for the motor. Over there. Yeah, 48 Hertz. Now if I take it up to 100 Hertz, you can see we're still at 220. But what has happened here is our current has halved. Okay, that's what's called field weakening. It's done on DC and induction motors. In the case of a DC motor, you keep the armature voltage constant after a certain point, and you reduce the field, the magnetism in the field, and the armature speed increases. So once again, torque decreases as speed increases, so it's constant power. In this case, the same thing, constant voltage, but your current starts to come down, and that's what the current reducing looks like over there. So it's quite normal to do this with induction motors and variable speed drives. One's just got to be aware that you're in constant power at this point. So you've got to rate your motor to suit the power that's going to be absorbed when you overspeed it slightly. Generally we go for a maximum of about 70 Hertz, which would be about 40%. Absolute maximum we see is maybe 50% that we go into field weakening. it's not really practical or beyond that. So we go up to about 70-75 Hertz if we do need to overspeed. That's usually done on constant power loads as well. You're not going to achieve this on a square law load. It doesn't work very well, because obviously a square law load is going to be demanding more power exponentially at that point, and you're in constant power, so it's not going to work. It's something like a conveyor that you just need to overspeed a little bit. Maybe your gearing or something isn't quite right, or the operating conditions require it, and then you overspeed it and it works. It's not a problem. So that's the story. So I'm going to wrap it up here. That was a brief talk on field weakening and what the effect on the motor current looks like. You get to see it on a scope, which is rather nice. So I'm going to keep it a short video here. Ladies and gentlemen, thanks for being here today. Take care, I hope you enjoyed it. See you next time for more stuff. Cheers.